horizontally, what happens?
It goes further away from the reference point,
Yep,
and then it comes closer to the reference point.
yep.
And then it goes away from it again.
Okay, so here's what our position time graph has to show. It has to show starting at the reference point, going away from the reference point. Now, when it goes back to the reference, when it goes back, does it go all the way back to the reference point? No. It goes part way, and then it does what? Then it goes forward again. Okay? So, now we'll shift this over here again. So now we're going to do horizontal position
What?
versus time. So Miss Canizzo, what's that going to look like? Where's it going to start?
The bottom?
At the reference here? 0, 0?
No.
Yeah,
Yeah.
yeah.
Okay.
Because we said that was the reference point.
Yeah.
So it's going to start here.
Okay.
Then what's it going to do?
Go out further. Yeah.
Okay, probably something like this.
Yeah.
Then what?
And come back.
Maybe something like this. Now it's going to go all the way to here.
No.
Okay,
Just
then
like
what?
a little bit. Go back up again. Just
Okay.
poquito.
Yeah. And then go like this.
Yep.
Everybody cool with that? So it shows us starting at the reference point, going away from the reference point, coming back towards the reference point, and then going away. Now, here's what you have to be very careful about. On your vertical position versus time graph, when this thing starts up high, that's physically where this is. It's up in the air. And it's going down, and then it's going up, and then it's coming down. With this one, don't look at this graph and go, oh, it's going straight, and then it turns right, and then it turns left again. Okay? I can't tell left, right, up, down. The only thing I can tell is that this thing, like let's say here's the car, the only thing I can tell is that it's going away from the reference point, it goes back towards the reference point a little bit, and then it goes away again. I cannot tell left, right, up, down. The only thing I can tell is that it's going away, it's coming back, and then it goes forward. That's all I can tell. How many direction changes? 2. Here and here, because that's when I can draw tangent lines that show that they are 0. Now, if all you saw was this graph, okay, if all you saw was this graph, could you conclude that there is a loop? No. How could you do this without a loop? Without a vertical loop, I should say.
Just like turns around.
Yeah. Okay. One option is that I
Put it in reverse.
started here, right? And then I put like an S curve in it, where I would be going away, it would come back to the reference point, and then it'd go forward again. The other option is that I could put like a horizontal loop in it, okay, where it would go forward. So that would be like what's on that second part of that back part, where it's going away, it's coming back, and then it goes forward again. This is going to be one of the questions on the assignment that you're going to have today. But if I look at both of these things happening at the same time, so if I were to look at what's happening in this time interval between here and here, oh, I'm going up, and on this one, I'm going up and I'm coming back down. On this one at the same time, I'm going forward, I'm coming back, and then I'm going forward again. So if I combine both pieces of information and realize that I'm going up and coming down, I'm going forward, I'm coming back, I'm going forward again at the same time, the only way these two things exist is if I have a vertical loop. Okay? Now, if I only have like this one, like let's say I just build the roller coaster with the hump in it, without the loop, then this graph would just be a curved line like this. And you wouldn't get a change in direction because it would just be going forward. Okay? So, when you superimpose both ideas, that's when you realize, oh, If you don't know the shape of the roller coaster, but when you impose this idea against this idea, oh, there has to be a loop. Okay? Got it? Good? Okay, let's go back. Take the cameras and let's roll. Go that way. Go that way.
Okay. Cheese. Oh god, this is gonna be terrible. Where does this plug in at? Oh wait, found it.
Okay, yes, just go on that right side behind you.
How's it feel being the star of your own show?
I'm so confused how this works.
Huh?
Oh, hi.
I think that works. Okay.
Move this way. Good enough.
Okay. So here's the last thing that we have. So when you're talking about a position time graph, literally there are only two options that you can show on a position time graph. Okay, and only two options. Either you have some kind of straight sloping line like this, which indicates that you have constant velocity. And if you want to find the velocity at any point from here to here, all you have to do is find the slope of the line. So let's just say this point, I'm just going to make up some numbers. So let's say that's 2 seconds and 4 meters, and let's say that this is 6 seconds and 10 meters. So if I know these are these 2 points, 2 seconds, 6 seconds, I can find the slope of this line. I can take 10 minus 4 and get 6. I take 6 minus 2 and get 4. So I would have 10 meters minus 4 meters, and then 6 seconds minus 2 seconds. So when I find this, okay, this change in y, this is my displacement. Okay? So remember, displacement is a vector quantity because it shows magnitude and it shows direction. So one way to calculate displacement is you just take position final minus position initial. Okay, hey, that's going to be 6 meters. I figured out how long it takes. So this is going to be 6 meters divided by 4 seconds, which is like 1.5 meters per second. So here's what's important on this. It's subtle, but it's important. If I pick 2.1 seconds, if I pick 3 seconds, if I pick 4 seconds, if I pick 5.31427 seconds, doesn't make any difference. Any point in time along this line has the exact same velocity because it's constant, it's not changing. Doesn't make any difference which point in time I pick because this all has the same slope, it all has the same velocity. Okay? Time doesn't matter. Now, over here on a position time graph, it looks like this, where this line is curved. Now, my velocity is always changing. So, how do I know that my velocity is always changing? Slope is always changing. I have no constant slope in any of this. Okay? This slope is continuously changing. So if let's say that this point in time right here is, let's say that that's like, I don't know, 2 seconds. So if I want to figure out how fast I'm going at exactly 2 seconds, I can't find the slope of the line because the line is curved. There's like, whoa, that's kind of a crappy deal. Okay? But what you're going to do, and this is what you're going to do on your assignment, you're going to come in here and you're actually going to draw a tangent line. You're going to take a ruler and you're going to draw a tangent line that touches the curve at whatever point in time I tell you. Okay, so I'm going to ask you, what's the velocity at exactly 2 seconds? So you're going to go to 2 seconds, come up here. Now, this is where there's some variance because how Riley draws her tangent line versus how Ellie draws her tangent line might be a little bit different. But what you've got to do is imagine that that's part of a circle, and there's the radius to that circle, and it's going to be at a right angle to the radius at that point. Now, after you've done calculus, and if you know the equation that generates the line, you take what's called the derivative of it, and then you can find the slope of that tangent line at that point. But we're not going to do that because all I want you to get is the idea that, oh, I can draw a tangent line, I can find the slope of that, that's what I need to do. So, now, let's just say that this point over here is like 4 meters, right? Now, here's what you cannot do, okay? Here's what you cannot do. To calculate the velocity at this point, you just cannot take 4 meters and divide it by 2 seconds, okay? Because if you do that, if I just take 4 and divide that by 2, I would get 2 meters per second. Now, first off, with this line coming down like this, what sign should the slope of that be? Positive or negative? Negative. So if I just take this point, that distance, 4 meters, and divide that by 2 seconds, number one, I'm going to get a positive velocity, which doesn't match up because I've got to have a negative velocity. Okay? So right away, I can't do that. How many points do you have to find the slope of a line? 2. I can use this as one of my points. Okay? I can use that as one point. But I've got to pick another one. So let's say that this point in time out here is like, I don't know, 4 seconds and 0 meters. Now I have 2 points. Now I've got 4 meters and 2 seconds as one data point, and then I've got 4 seconds and 0 meters as my other data point. Okay? Now I can calculate my displacement. Oh, my displacement is going to be 0 minus 4, because remember, your displacement, listen to me, listen to me, listen to me. Your displacement is always position final minus position initial. So my displacement is going to be like 0 minus 4. Okay, so that's going to be negative 4 meters. And then I'm going to divide that by 2 seconds. I'm going to get negative 2 meters per second. Now that works, okay? Because now I get a negative sloping line, which is what I should get. And I've chosen 2 points to find the slope of the line. So what's going to happen on your assignment, I'm going to give you data points to plot off of a roller coaster. And you're going to generate, and it's going to be some curved line. And what I'm going to do is I'm going to pick a point and say, okay, hey, what's the velocity at this instant? Now, let's say I go to this point right there, which is 3 seconds. Let me clean this up again a little bit so we're not so completely. Okay? So let's say that's 3 seconds. And I say, what's the instantaneous velocity at 3 seconds? So at 3 seconds, you'd come in here and you draw a tangent line like this. So when you have a tangent line like this, what's the slope of a horizontal line? 0. So why does that have a horizontal line? That tangent line is horizontal at 0 seconds, or at 3 seconds. What does that indicate? What's it doing? It's stopped, because now it's going to change direction. Okay? So when you get done with this assignment, if you have not drawn some lines like this, where it's horizontal, okay, you've done something wrong. Okay? When you get done, you should have some horizontal lines, and I'm going to ask you, what's the significance of that horizontal line? And you can say, oh, that tangent line is horizontal because that's when you're changing direction. Because you're switching sign from, in this case, a negative velocity to a positive velocity. Now, you draw tangent lines. The only time you draw tangent lines is when your velocity is changing. Okay, that's the only time I'm ever going to ask you to draw tangent lines. And then what that gives you is what we call instantaneous. I'm going to run out of room. Okay. That's going to get you, that's a long word. Right? Yeah, velocity. Close enough. Okay. So, or you can say that's the velocity at a point in time. So, I will only ask you to draw tangent lines, number one, when it's curved, and then I'll say, what does that get you? It gets you an instantaneous velocity. Because if you have like a straight sloping line like this, when you have constant velocity, you couldn't draw a tangent line to this if you tried, because there's no curve, okay? So this instantaneous velocity here is just whatever the velocity is, whatever the slope of that line is. So you only draw tangent lines, okay? Listen to me. You only draw tangent lines when the velocity is changing or the slope is changing, and that gets you that instantaneous velocity, okay? Got it? Good. Okay, so let me hand out the sheet, which is just got it.
I got my test in my phone.
Huh?
My test in my phone.
What?
Test, phone, picture.
Yeah, but right now I'm missing a stack of papers.
Okay,
That is right here.
cool.
Now, you out in the studio audience should already have this. It says a tangential tour of rock and roller coasters. One of my better titles.
Your title was making things.
Oh, that's right.
I'm gonna take mine.
Okay. So let me kind of get you through what you're going to do with this tangential tour. By the way, when you send this in, just title this roller coaster worksheet. So when you send this in, just call it roller coaster worksheet. And y'all are doing a very good job of like putting your last name and then a 1 and then roller coaster. That makes my life so much simpler. Thank you very much. Okay, so here's what you're going to do. You've got 3 columns: time, horizontal position, and vertical position. So I'm going to take you through the 3 graphs. So I'm going to give you a sheet of graph paper. If you want, you can just divide that graph paper into thirds and put all 3 on one graph. If you go, oh, Burkamp, I like bigger graphs, okay? I can give you more graph paper if you want, okay? And you can do half. If you really want to kill trees, you can put 1 on each sheet of graph paper. It's up to you, okay? I don't care. But here's what, let me tell you what the graph's going to look like. So down here on number 1, it says, plot a position time graph for movement along the ground, describe the shape of the curve. So on number 1, what you're going to do is you're going to plot horizontal position versus time, okay? Now, you're going to go all the way through 24, so you've got to set up your time scale so you can go from 0 through 24 seconds, okay? So that's going to be a little length of time. So at time 0, your horizontal position is going to be 0. Okay, so that's 1 data point. And then at 1 second, you're still at 0. Okay? And then at 2 seconds, you're at 1, and then you're going to go, okay? So when you get done, trust me, this graph is going to look something like this. So your first horizontal position versus time graph is going to look something like this. Now I want to say, describe the shape of the curve. You're not writing your doctoral thesis. All you have to say is something simple. You can say it rises, it falls, it rises. If you're a math nerd, you can say, oh, it looks like a cubic root function. okay? If you're really a hardcore math nerd. If you're a biology person, you go, oh, it kind of looks like a snake. Here, okay? Here's the main thing. It's not a stick, okay? It's not a straight sloping line. So then, that begs the next question. On number 2, is the velocity constant in the horizontal direction? Explain your answer in terms of slope. So, based upon this, is the velocity constant? Riley.
No,
Why? Because what's changing?
the direction.
Yeah, and you're changing the slope, okay? So there's your answer. That's all you have to do. Now, on number 3, 3 is where you're going to have to draw the tangent lines with a ruler, okay? Now, if there's one graph that you might want to draw big, it would be this first graph, okay? Because you have to put a lot of stuff on this first graph. So if there's one that you do want to maybe draw a little bit bigger, it might be this one. So here's what's going to happen. You're going to go to the 8-second mark, okay? And you're going to draw a tangent line. So what you're going to do is that you are actually going to take like a ruler, and you're going to go to the 8-second mark, and you're going to come up here, and as best you can, you're going to guess what a tangent line would be, where it would only touch that curve at one point. So you're going to come in here, and you're going to draw a tangent line that only touches the curve at that exact 8-second mark. Okay, so that's the first thing that you have to do, is take a ruler and draw that tangent line. The second thing you're going to do is you're going to find the slope of this line. Now, oddly enough, in case you haven't figured this out, down below I tell you, okay, draw the tangent lines, show calculations of slope. So you're going to pick a couple of points that are on this line. You can use 8 seconds and whatever that position is. You can use that as one of your points. Okay, that's cool. You can use that as one of your points. But you've got to pick another point on that line as well to find the slope. So when you get this slope, do not leave it as a fraction. Okay, right? Do not leave it as a fraction. For the love of all things, do not leave it as a fraction. You should have the units with it. Okay, when you get done, you should, oh, here are the units. Oh, that's kind of cool. Then you're going to do the same thing at 12 seconds. So you're going to come out here to 12 seconds. You're going to draw a tangent line like that. Now, what you should see is that your 8-second mark has a positive velocity. Your 12-second mark has a negative velocity because of the fact that this thing has changed sign. So when you do those calculations, if you don't get a positive and negative slopes, you've done something wrong. Okay? Now, everybody's is going to be a little bit different on here. This is why I can only grade your process and not like the answer, because everybody's is going to be a little bit different. On the back side, when you get to number 4, at the 9 and 13-second marks, you're going to draw tangent lines. Let me give you a hint. 9 seconds is going to put you at a relative maximum. 13 is going to put you at a relative minimum. Okay? Draw the tangent lines. Okay? If you draw those right, you should be able to look and go, oh, clearly this is the slope of the line. So on 9 and 13, you don't have to show me the calculations of the slope. More importantly, I want you to know why those lines are what they are at those points. When you get to question number 5, on question number 5, what I want you to visualize is that's what we talked about back there at the roller coaster. Visualize that you're looking down on top of the roller coaster. I don't want to hear going up, going down, anything like that. All I want you to describe is what you would see in a horizontal motion on the roller coaster. Okay, that's all. That's all. I do not. On number 5, tell me, oh, it's going to start high and then it's going to fall. No, it's not what that's about. You're looking down. The only thing you can describe is horizontal motion. Okay, that's it. Now, when you get to number 6, you're going to do vertical position versus time. So when you do the second graph, you go from 0 to 24 seconds. And then, oddly enough, it's kind of like Colorado. You're going to start off high, and then you're going to go down. So on that one, you're going to start here, and then it's going to go, and then you're going to see what happens there. So on the first graph, you're going to start at 0, 0. On the second graph, you're going to start at 0 and 11. Okay? Then, on this one, you don't have to draw any tangent lines. Okay? But again, I'm going to ask you, hey, is the velocity constant? On this one, when you get to number 8, okay, so visualize number 8. You're standing at the end of the roller coaster, and you see the cart way off in the distance. The only thing I want you to describe this one is what's happening vertically. Okay, so you would say, oh, I'm going to see the cart start up at the top of the roller coaster, and then I'm going to see it fall, and then you're going to look at your graph and you go, okay, how many times does it repeat that? Does it just fall once? Does it go up and down twice? What are you going to see? So don't tell me, oh, it's going forward, it's going back. Oh, no, no, no. All I want you to describe is what's happening in the vertical motion. That's it. Okay? You see this thing coming towards you. What are you seeing vertically? Now, here's the last graph that you're going to draw. On number 9, you're going to draw your third graph. Number 9 has nothing to do with time. This is all about your two positions. So on number 9, you're going to put your horizontal position, oddly enough, on the horizontal axis. You're going to put your vertical position on the vertical axis. Now, this is the only time you have to do this. What you have to do is that you have to let both scales be the same numeric value. So like if you're going to let one square here be 2 meters going this way, you have to let one square be 2 meters going up. I don't care what the scale is, but they just have to be the same. It doesn't have to be that way in the first 2 graphs, okay? But it has to be the way on this third graph. That way, because this has nothing to do with time, and you're plotting the dimensions, you want to make sure that your dimensions on both axes are the same, okay? I don't care how you set it up. You want to let one grid be 5. I don't care. But then you have to let one grid be 5 meters going up this way. Okay? That's going to be the most critical. Now, when you get to number 11 is the culminating idea. So on number 11, you're going to go between 7 and 15 seconds. Okay? Listen to me. Not 7 and 15 meters, but 7 and 15 seconds. And you're going to look at what's happening vertically, and you're going to look at what happens horizontally. So here's how I want this answered on number 11. You're going to go between 7 and 15 seconds on the horizontal graph, and you're going to say, this is what's happening between 7 and 15 seconds. Is there a direction change? Is there more than one direction change? Are there no direction changes? Okay? So between 7 and 15 seconds, you're going to say, this is what's happening horizontally. Then you're going to go between 7 and 15 seconds vertically. Is there a direction change? Is there not a direction change? Is it only going up? Is it only going down? What's happening? So you're going to go between 7 and 15 seconds vertically and say what's happening. Then, once you figure that out, then you're going to describe what part of the roller coaster are you in. Okay? So you would say, okay, hey, horizontally, it's only going in one direction. Vertically, maybe it goes up and comes back down. That would mean that there's a hump in the roller coaster. Okay? Maybe you get direction changes in both. Oh, maybe there's a loop. Oh, maybe nothing happens and it's just like the flat part of the roller coaster. Okay? You don't know. But what you're going to do, and listen to me, you have to reference both graphs. So you're going to go between 7 and 15 seconds here. This is what's happening horizontally. 7 and 15 seconds here. This is what's happening vertically. Based upon that, this is where it is on the roller coaster itself. Then you're going to do the same thing between 17 and 24 seconds. So you're going to go out here between 17 and 24 seconds. And you're going to say horizontally, this is what's happening. Between 17 and 24 seconds, you're going to say this is what's happening vertically. And then you're gonna go down to the roller coaster and go, oh, this is where it is on the roller coaster. Okay? Got it? Good. Okay, so this assignment, this roller coaster is going to be due tomorrow. I'm also going to give you all the assignment that I'm giving tomorrow in class, which is going to be due on Monday. So this assignment for you guys is due tomorrow. I'm also giving you the assignment that I'm going over in class, which is going to be due on Monday. Now, if you want to begin to plan next week, okay, a week from tomorrow on Friday is when we have the first kind of big test, which is going to be that velocity test. And that's one I'd like for you guys to be able to come in, even though it's your off day. If you guys could plan on coming in, and then that way I can test everybody at the same time. If that doesn't work for you, we can make other arrangements, okay? But I'd like to kind of have some cohesiveness where I can test all my kids at the same time. We'll talk more about that later, but if you want to begin to plan, so a week from today is when we're going to have kind of the first kind of bigger test on velocity, okay? All right, I'm done. I'm going to hand out that assignment. I'm going to give you all some graph paper, and here we go. So, Zoomers, we're out. So, go ahead and just shut down the meeting. So this one is what's going to be due on, I'm giving out tomorrow, which will be due on Monday. Yep. I'll just give you all a couple of sheets of graph paper.